Hi, everyone. Thanks for coming here today. I'm Henry Stern, and I'm excited to talk about expected consensus, which is a Nakamoto-style consensus protocol developed for use in Filecoin. This work is being jointly done by the Filecoin research team. It was initially developed by Juan Benet, Nicola Greco, along with Jeremy Johnson, and now Wyatt Davia and myself. So since you're here today, I assume you have heard that we're building a decentralized network for file storage called Filecoin. And an important thing to remember is that Filecoin is actually a number of protocols and primitives that were developed in parallel to create this working system. Some of the components have existed for a long time, and others don't exist yet or are being developed by ourselves or others. But the idea is to try and make this as modular as we can so we can keep upgrading the protocol as research advances. And this is sort of part of the pipeline from idea to product that has all of these feedback loops in all directions. So when the system was first thought up, there were a few potential ways to go. The gold standard was sort of fully permissionless storage-based proof of work. This is sort of not exactly the right setting for Filecoin in that we want a semi-permission network. Users coming on need to basically agree on deals that they'll be making to store data ahead of time, so it's not a fully permissionless setting. So then we can turn to sort of Byzantine consensus-style protocols like Algorand. But unfortunately, those typically have high communication complexity and a lot of overhead. So it's not exactly the right solution for us either. And finally, we have proof of stake, which is a sort of area that's been developing for the last few years, where one coin is equal to one vote. And in our version of the world, we sort of want 1 gigabyte hour to be equal to one vote, or something like that. So given advances in the space and this flexibility it affords us in a modular architecture, we sort of went for this option. So before going too deeply into expected consensus, I want to talk about how this sort of fits together within the context of Filecoin, because I think it's kind of important as to how we've been thinking about this, and also in the problems that we sort of face trying to do research on live production systems. Our interest today is the consensus algorithm, which is the decentralized state machine at the center of Filecoin. It tracks who's storing what on the chain or in the network. It allows new participants to join, and it allows old contracts to expire. You can think of it as something like this. At the bottom, we've got the Filecoin protocol, which for our purposes just creates these like magical proofs of space-time that ensure that actors are storing unique data replica over time. Those feed into the next layer up, which we call storage power consensus. Basically, storage power consensus takes these proofs and creates and maintains a power table that accounts for miners' power, the storage they've contributed to the network, relative to the network as a whole. There's a number of really cool consensus questions around SPC, but that's a topic for another talk. And finally, what brings us here right now, expected consensus. Like Sana, expected consensus takes a look at the list that the storage power consensus provides and tries to reward miners fairly. So I'm going to move away from the Sana analogy for a second and talk about blockchains. EC is an incentive-compatible proof-of-stake protocol that takes in a list of miners and their relative power at regular intervals and outputs block that reflect an up-to-date state of the network. We're going to talk about the model for a quick second. We have a few requirements for Filecoin consensus. It needs to be live, meaning it keeps progressing and we're thinking about this in a sort of eventually synchronous network setting. It needs to be fair, meaning it rewards miners based on the power that they've contributed to the network. Verifiable, meaning any observer on the network can actually make sure that fairness is enforced. And finally, it needs to be consistent, meaning all miners end up agreeing on the state of the chain at some point in time. And then, because we're building a system in the real world, it needs to deal with three types of participants. Honest participants who follow the protocol sort of to the T, rational participants who are in it to make the most out of this and are happy to deviate from the protocol if that's in their interest. And finally, adversarial participants who are trying to break protocol guarantees at all costs. And again, I want to emphasize that because we're working in the context of a real-world system, we actually spent a lot of time thinking through the rational miners' incentives. And this brings us to an important notion, which is incentive compatibility. And our claim is that a protocol can be deemed incentive compatible when it's impossible to distinguish between honest miner behavior and rational miner behavior. And that's what we're shooting for. Now to get into expected consensus itself, expected consensus is really two protocols. It's cryptographic sortition to do leader election, and it's chain selection that allows for state updates. Jumping into secret leader election, we have a few requirements. So secret leader election is what I call our cryptographic sortition, but it needs to be secret or globally unpredictable, meaning no one who's looking at the chain can guess who the leader is at round R until that leader has put out the block and revealed themselves. And this is really important because if you get to know who the leader is before they've announced themselves, then you can DOS them, you can bribe them, you can do any number of things that sort of break fairness. Fairness now is the fact that on expectation, leaders should be elected in proportion to the power they've contributed to the network. And this is coming from our power table that I mentioned earlier. And finally, it needs to be verifiable, meaning you can prove that you're a leader in some sort of unequivocal way. So this is actually pretty straightforward in the context of Filecoin. Thankfully, we have a chain, so we can actually generate sort of seeds, random seeds, by sampling from the chain. So that's what exactly what miners do. Miners take seeds from the chain, and then they pass it through a cryptographic compression function. We use SHA-256, and then a verifiable random function in order to make this unpredictable. That yields a ticket, and then they compare this ticket to their power in the power table. If the ticket is smaller, then they've won and they get to publish a block. If it's bigger, they have to wait for another leader to reveal themselves. Again, the important points here are that the common seed is available to everybody, meaning everybody can sort of do this computation again in the future to verify that the leader's actually been elected. And then the VRF allows us to make the election unpredictable. You can't know ahead of time who the leader is. And those are two of the important properties that we wanted. What's actually happening here with VC, though, is that we have really two chains. We have a blockchain, and then we have a ticket chain that are both used as part of the protocol. And for now, our construction draws the seed from the last block. This is kind of useful. And by this, I mean basically that you're sampling your seed from the block prior to the one that you're building on, or to the block you're building on. This is kind of useful because it ensures that leader election is not locally predictable. What that means is that if you were drawing from farther back, you might be able to know that you're going to win ahead of time, which we want to prevent because it makes it easier for you to mount an attack. In this sort of setting, you have to be basically running your attack continuously in order to win. If you knew you were going to win at some point, you could time your attack precisely, and that makes sort of an attack on the protocol a little cheaper. Finally, there's an issue that comes up here, and this sort of motivates the last piece of our construction. Because this isn't actually proof of work, it's actually fairly cheap for a miner to generate tickets repeatedly until they've won. Like running a VRF is pretty cheap computationally, so a powerful miner will be able to generate tickets and unfairly win the election. And the point of our system is that we want to sort of respect the power table, in this case, determined by storage, not by computational power. And so we introduce the last element, which are VDFs. And VDFs allows to sort of force miners to synchronize and wait around between every lottery ticket draw. We can't count on clock synchronization in this sort of semi-permissionless setting. And yeah, that really helps us make sure that leaders don't do what is happening right here, which is called grinding, trying multiple options until you get an output that helps your case. So this is our sort of final construction for now, which is a chain VDF and VRF that generates a ticket at every round in the protocol. We have a concept of rounds, which ensures that storage power and not computational power is the basis for fairness in EC, or specifically in EC tied to a power table that's tied to storage. And it also gives us liveness, which is it allows the protocol to proceed if no one wins in a given round. And the simple way to do that is basically, if I'm a miner and I run my VDF VRF construction and I get a ticket that leads to a loss, I wait until I hear from somebody else whether they've won a block. And if they haven't, then I can just run the VDF-VRF construction again until somebody finally wins. We call this mining null blocks in the context of Filecoin. So now we're getting to why this is called expected consensus, and you may have sort of caught the rub. The issue is that in the same way that we can have no winners in a given round, we can also have multiple winners in a given round. And so in this case, we have Alice, Bob, and Eve, and we have both Alice and Eve winning a block because of the VRF. Both of their seeds are different, and so each winner sort of is independently doing this leader election, and we can have multiple leaders elected in any round. And this leads us to this sort of second really important component of EC, which is chain selection. So for chain selections, we sort of follow a simple rule. Forks are bad, convergence is good, and sort of batching blocks together helps push the blockchain to converge. So we're using a block DAG structure like in Phantom or Spectre so that we make use of all the computation that was sort of, or all the storage that was generated in a given round. And we call this set of blocks a tip set. So we're batching blocks that are outputted in a given round and using that tip set to mine off of, as opposed to mining off of an individual block. Again, why do we want to do this? Well, because we have multiple parents, we can get more sort of attempts at grinding or at mining off of a subchain, which leads to longer convergence. And yet, we also don't want to waste that storage that people have put out. So I'm repeating myself, but we deal with that by having miners combine their parents to try and rein the sort of forking factor in. There are three details that I want to touch on really quickly that sort of help, again, sort of control this convergence a little more. One is chain weight. One is using minimum tickets to reduce seed grinding. And one is a rule, which is all tipset members must have the same parents. And I'm going to go into these in a little bit more detail. So, sorry. The first rule, yeah, okay. The whole point of having multiple blocks is to ensure that we're not wasting work and people get rewarded for the work that they've done. More blocks, in our case, means a heavier chain. And so basically, you're incentivized to, the protocol dictates that users choose the heaviest chain. And so again, this is Ghost T. It's the greedy heaviest observed subtree variant of longest chain protocols, where we account for multiple blocks by assigning weight to them. But this basically means that our chain is going to converge towards the most work performed, which is what we were going for. Now, I mentioned grinding earlier. There is an issue, which is if you have a tip set with, say, 3 blocks in it, which block are you going to sample your randomness from? And that gives you sort of an opportunity to have 3 runs at leader election, even though you should only be getting 1. And so to help sort of reduce the number of forks, the protocol dictates that the miner must use the smallest ticket in the tip set. In this case, we've got A's ticket is smaller than B's ticket is smaller than C's ticket. So from the protocol, the winner would include A, B, and C as the tip set for their next sort of produced block, but would prove her election using A's ticket. Now, this is the sort of last rule that I mentioned, which is all blocks in the tip set must point to the same parent. And this sort of actually implies that all blocks in a tip set will have the same height at the end of the day. And again, this helps sort of simplify the design and make sure that we limit, in this case, we're limiting block inclusion in favor of convergence. There's a last detail I'll mention really quickly, which is that we use slashing in order to sort of punish provably divergent behavior. And as an example, if you release 2 blocks in the same height with different parents, meaning if you try to mine twice in a given round, you'll get slashed. So yeah, we have some work to do on formalizing the security proofs for the protocol. But like Nakamoto consensus, we probabilistically attain convergence in the limit. Another way to say this is that EC doesn't allow for long-running forks in time. Intuitively, it kind of follows from the fact that we have this sort of leader election process that limits the number of leaders who can publish blocks at any given point in time. If multiple win, we sort of push convergence by batching those together to have a single tip set that you're mining from thereafter, and sort of slashing to package all this together and make sure that people follow these incentives. And so here I'm going to take a step back and look at a detail or two of the design that feels important and that ends up being very important when trying to build this for sort of a network of rational miners who have sort of staked storage, hardware, and money on this system. But what you can see is that in spite of these rules, a rational miner actually has multiple blocks from which she can choose her ticket. For instance, I'm actually not going to go into this in too much detail, but here, Eve could use a tip set made up of A, B, and C, where A is the smallest ticket, in order to mine. Or she could use a tip set made up of B and C, where B is the smallest ticket, or she could use 1 and C. There's a detail as to why it works out that way, but ultimately, this isn't actually the full set. With these 3 blocks, Eve has 8 potential choices that she can mine off of. And while we use slashing to punish this behavior in theory, it can sometimes be really hard to distinguish sort of malign behavior from bad network connectivity. And we don't want to slash honest miners who just happen to be farther away from where the last block was published, for instance. And so in that sense, we're getting to a tricky sort of thorn in our side, which is that it's pretty rational to omit blocks from your tip set in order to grind. And the hope here is that you're going to make up for the lost weight that you got by omitting the block through sort of unfairly biasing leader election. Yes, you've lost weight, but you're winning more often. And so at the end of the day, you come out ahead rationally. That's the hope in any case. And so, our claim is that the rational behavior for a miner with a lot of compute is to mine tickets on every block produced in perpetuity, only pruning branches when they win at a given height. I'm happy to go into that a little bit more later. And this likely hurts convergence. And so we ran a few simulations, and yikes. This is a simulation run with 100 rational miners with equal power for 100 rounds, starting with a single block. So within 100 rounds, starting with a single block, I'm only showing part of the picture here, you end up with this kind of state tree. And again, this is sort of under potentially the worst kinds of assumptions. All of our miners are rational. None of them are actually following the exact protocol. But they're basically mining on any fork in which they know they won't get slashed, just in case it gets accepted at some point in the future. But because we're dealing with a real network, we want to focus on this rational behavior in particular, rather than assuming participants are just going to follow the protocol. So this kind of works out, again, in simulation. We see that our average number of forks at any given height increases with the number of miners participating. So in this case, with around 10 miners, we've got something like 7 or 8 average number of forks at a given height, meaning potential chains to choose from for every miner. But by the time we're at 500 miners, we've got something like 230, and at 1,000, we're up to 350. And obviously, this gets a little problematic. Again, we have sort of convergence in time, but the question is, how quickly do you get convergence? And this sort of gets even worse because you can assume that miners can sort of create Sybils and even avoid the slashing rule in which they're getting slashed for blocks at the same height. So yeah, I'm going to take a pause here and a bit of a step back to talk about sort of working on research for production systems. And I think this is something that sort of nags at the back of our minds when we're working on EC. It's really hard to get away from the fact that ultimately this has to be packaged into a working protocol that we're going to ship and that people are going to invest into. And so our goal is really to try and design the simplest protocol possible. We think it helps for ease of deployment. It'll help people build on top of it. But it also probably helps with security in that the simpler something is, the easier it is to see mistakes. And there's sort of a draw when you're doing these sorts of potential simulations, trying to see what rational behaviors give, to sort of make the protocol more complex time and again. And so for instance, with this, we looked into potentially making the weighting function more complex to account for this. We looked into solutions that involve checkpoints and more complex, and a final solution, which is a look-back parameter, and that's the one we retained. But I guess this is sort of a meta point about the usefulness of simulations in these contexts that sort of help guide our intuition towards what the sort of simplest optimal solution might be. So I'm going to talk about look-back parameters for a second, because I think it's a very cool topic. But so we have this rational miner who is now going to mine on every block that she sees because she can, and it's pretty not costly from a computation perspective. And so we choose to sample our seed from farther back. In this case, you can see the seeds coming from blocks in the past. That's the pink ticket on the left. And what's happening because we're sampling our seed from farther back is that mining across forks ceases to be an independent event. Instead of like potentially winning or losing on block A, potentially winning or losing on block B, and potentially winning or losing on block C, you actually have a global lottery now, which is you're going to win on every fork after the seed, or you're going to lose on every fork after the seed. And because of slashing, again, where if you get caught posting 2 blocks with different parents in the same round, that actually forces you to make a choice of a single block to put out. So we look at the impact of this, and it sort of plays out in simulation. We have, again, sort of with a look-back parameter that increases, our average number of forks at every given height goes back down to 1, which is what expected consensus should yield, a single leader on expectation. I'll take a second to look at how this impacts our construction. So we're actually now splitting our leader election process into 2 sorts of parts. One is a proof of delay, in a sense. This is the VDF VRF that we talked about that is sort of trying to prove I've waited the appropriate time before trying to get another ticket. And the second is sampling from K blocks back, a proof of leadership. I actually get to publish my block in this round. Yeah, I'm happy to talk more about the construction later, but we basically split those out and use them as separate events. The only thing you need to do as a protocol thereafter is make sure that the same number of rounds are run on both to ensure that people have waited the appropriate time before trying again. Finally, I'm going to end on a couple notes related to expected consensus and storage power consensus bundled together, because I actually think this is one of the most exciting parts of our work and some of the open questions that this sort of moves us into. But in a sense, I guess, I claim that the bundling of EC and SPC together yields a better approximation of proof of work than proof of stake alone. And taking just a step back for a second, we know proof of stake has a lot of issues. There's nothing at stake attacks, there's posterior corruption, there's grinding. But because here we're feeding storage proofs in sort of the underlying layer of the network, we're able to make stronger guarantees. At the end of the day, you can't really fake storage. And so with better primitives, we can actually improve proof of stake and move towards useful proof of work, which Filecoin is doing. Finally, I want to close on the fact that, as Juan mentioned, we are trying to do a lot of work and into sort of publishing our open problems. In fact, next week we're going to be opening up a lot of our research repos, so you can actually sort of tag along and see the work that we're doing on consensus in proofs and in other parts of the protocol. And so we've got a lot of really interesting problems that we'd love to collaborate on. These are open questions that will have a big impact on the field that we'd like to use for our protocols. And so I invite you to check it out and reach out if you're interested in working together. Thank you. Happy to answer any questions. I don't know how long that was.
I know that the VDF is a rather theoretical construction at the moment. I'm not aware of any actual practical implementation except for the square routing and whatever. How far along are you?
So this is work that luckily was done by other researchers in the field. So we're using a construction by Veselovsky. I think that's how you pronounce his name. And that's the one we're using. But this is actually an area that's extraordinarily important to us. Parts of our construction also assumes that VDFs will, if not be broken, at least be optimized. And basically, miners can attain more power by being better at running the VDF. And so that's something that we think about a lot. And part of the work that we're trying to do is, can you build this without a VDF or removing timing assumptions? And conversely, sort of to hedge our bets, we're also looking into, can we push forward sort of ASIC development for VDFs? Because this is going to happen. And so the best way to sort of protect against it is to make sure that every miner has access to that sort of tool rather than making it a thing where it's getting discovered over time and miners gain unfair advantage over the network.
And this is the project with Ethereum Foundation for the...
Exactly, yeah.
ASICs.
So shout out to, there's a VDF day tomorrow and for the days following that talks about this topic specifically. And obviously it feeds into consensus. And I think this is part of what's really cool about these systems is that they are a cobbling together of primitives with sort of incentive compatibility, and there's a lot of interplay between them.
What is tomorrow?
Tomorrow is VDF Day, so it is a sort of workshop that's built around specifically addressing constructions in VDFs and how to make them better, and it is run by a project that we're working on with the Ethereum Foundation towards these goals.
Yeah, we can post the details for VDF Day and so on later on during lunchtime. Also wanted to mention, accepting consensus is a bit generalized, where one construction is with the VDF. If you had some other way of thinking about power that gave you, for example, if you're in a model where you're totally fine using something like SGX, you could use that to have a trusted notion of power. Expected consensus just deals with, given that you have some power construction that also delays you, then how do you build consensus? So VDF is the way that we want to go because we don't want to use SGX. But if you had other mechanisms, right? Like if you had like a physical process that you were sampling from physical reality that gave you some delay that was that you couldn't use for multiple potential forks, then that's the same. You can use that.
To add to this point, basically we're using VDFs as an approximation for a random beacon. If we had a better random beacon, even an off-chain random beacon, one that didn't depend on VDFs, we'd happily swap it in.
The guys from Infinity are working on this basically signature aggregation, which intends to work as a random beacon.
Cool. Yes.
And so why are you using VRF after VDF? Yeah.
That's a really good question. There's a very specific reason why that relates to sort of ASICs and VDFs, why we chain them together and we don't use sort of a VRF chain independently from a VDF chain. With that said, I think using VRF after VDF or before VDF, they're actually interchangeable in both cases. Yeah, I don't think it makes a difference in terms of the construction. Well, so my issue with that, the reason why you need the VRF is that if you just use the output of the VDF alone, so you have a VDF chain, then if you assume that somebody can speed up VDFs, they've broken the system entirely, and they can just simulate the chain in eternity. You add the VRF in because there are other miners participating, and so hopefully the other miners' randomness stops the simulation from being accurate after some time. It's not that's not an exact answer to your question, but that's why we don't do a pure VDF chain.
So the input of the VRF is what then? The output of the VDF, just that.
Yeah.
I mean, I was thinking, can you keep the other one? Can you use VRF and use the output of VRF as a random seed for the VDF?
I think you can, but I'm not sure what does that gain you.
Like VRF, I think that it's closer to the hospital that
I mean, Phantomet is a great example of a protocol that does it in that direction, and it's something.
Because like VDF is kind of like a fallback for liveness. Like ideally, we wouldn't want to use like VDF. So that's why I'm wondering, like this sense, like I'm not sure I understand what we use contact.
Yeah. One of the reasons we use a VDF as well, it's not just for a fallback for miners.
Yes, yeah, exactly.
It's also to delay miners.
Right.
So
yeah.
we claim it is not a whole different other thing. It is not rational to wait the block time. So if you have a lot, contrary to what other people have claimed, if there's a lot of transactions around, you're gonna speed up the chain. So we want the VDF to force the delay of the block time, so that a clique of miners that are close together don't suddenly speed up way beyond the rest of the network. And that's one of the main reasons for VDFs in our case. The liveness thing is also a very great way to go around FLP.
In some sense, we are using VDF as a proof of work, like kind of equivalent, right?
Kind of, yeah.
But the speeding up parts and the fact that it isn't rational for miners to wait probably has an impact on like centralization of the network, where if you want to allow people in places with forced connectivity or so on to do it, actually having a minimum round time that we can enforce seems really important to us.
No, I mean, yeah, I understand why you use the VDF first, but then I'm like, is it actually useful to use the VRF after it?
Right.
But this,
Yeah, what Henri said is really important, which is that you don't just want to see a VDF in the beginning and everybody have the same clock. You want to have this continued resampling together, so that, again, if the VDF is potentially broken or accelerated in some way, you can use the latency of the propagation of the blocks to help you get randomized guessing.
Okay, so everyone has the same VDF but not the same VRF?
Exactly.
Okay, makes sense.
To me, actually, that's like the other flip side of the question. So between having fake input to VRF and a fake input to VDF, because you have to VRF before VDF, it's made it like you have to put it the other way around. The reason I thought having VRF before VDF was easier, then it's more difficult to fake the input to the VDF by having VRF before that. So for that reason, I would put VRF before VDF.
Yeah.
Thank you.
Thanks.
Do you have any something to talk about the physical, like the simulations? Is that code available somewhere?
Yeah, that code's on GitHub. So when we release, we really work hard to make everything accessible so people can help and work alongside this with us. So we actually have a couple simulations, and they'll be in the GitHub repos that are linked from there. So you can actually see what sorts of miner assumptions we're making precisely, and how we're modeling all of that. Part of the work that we're going to do moving forward as well is swapping out to more realistic assumptions. We sort of took a, maybe not worst case, but a not great case of 100% of the network is rational, no one actually follows the protocol, which, in truth isn't going to happen. You're going to have some people who are just using the vanilla protocol and not adapting it to their own needs. And so we want to also see how this performs with different proportions of honest, rational, and adversarial miners. So help us build that, please. Thank you.